Welcome to EPG Pathshala lectures on numerical method. We are going to consider a module on iterative methods for solving systems of linear equations. The module objective, learning objective for this module set are iterative methods for systems of linear equations. In that we are going to consider two methods, Jacobi and Gauss-Seidel method. Convergence of these schemes we will be talking about, and computational aspects of these schemes also. These methods we will try to consider. Introduction is that in the module 12, we have already discussed some direct methods for solving a system of n linear equations in n unknowns given by x bar equal to b bar, where A is n cross n matrix with rank n, that is non-singular matrix, and b bar is any non-zero vector in R n. So, again we are considering this system which is ensured to have unique solution. In this module, the iterative methods for finding solutions of to a system 1 will be discussed. The iterative methods generate a sequence x bar k of approximations to the solution x bar of the system, starting with some initial guess x bar 0 and using some iterative scheme. This is what we have already said in the earlier module. If the existence and uniqueness of a system x bar equal to b bar is assured, then any of the direct methods always compute almost the exact solution except for some round of errors. However, time required for computing the solution becomes prohibitively increases as the size of the system increases. So, if n increases, it is order n cube asymptotic time complexity we have said, and this time also increases very rapidly and it goes beyond certain limits. So, in such cases the iterative methods may be useful to get an approximate solution with desired accuracy with relatively less effort. So, that is why we are doing iterative methods. Getting an approximate solution instead of an exact solution is not a matter of big concern. The reason is, as mathematical models for most of the real world problems leading to a system of linear equations have inherent simplifying assumptions as well as measurement uncertainties, and therefore, there will be anyway some kind of near about solutions only we are going to get, and therefore, this is not a big limitation, not getting an exact solution. The two major issues related to iterative methods are convergence of the sequence of approximations x bar k to an exact solution, and at what rate you are converging to the convergence of this sequence. So, these are the two major issues here in the iterative methods. So, how do we generate iterative schemes? So, simple way to generate iterative schemes is that starting with some initial guess x 0, we generate a sequence of approximate solutions using some kind of a scheme like this: x bar k equal to t into x bar k minus 1 plus c for k equal to 1, 2, 3 and so on and so forth. Selection of the fixed matrix T and a vector C bar makes the difference in the iterative methods. To get such a T, we split A as lower triangular matrix L, diagonal matrix D and upper triangular matrix U, where L is given by lower triangular elements here, all other elements 0. Here we get only diagonal elements and all other elements 0, and here we get upper triangular elements, and all these elements are of matrix A only, and therefore, when we add all of them together, I will get A. So, we are doing that. So, naturally we will be getting now, see, also note that if the diagonal matrix D is non-singular or equivalent to A I is not equal to 0 for all I equal to 1 to 3 up to n, then D inverse exists and is given by 1 by A 1 1, 1 by A 2 2, 1 by A n and so on and so forth. So, D inverse will exist like that. So, in such a case x bar equal to B bar. Now, I am writing A equal to L plus D plus U is equal to B bar. So, this is possible if and only if this happens. If and only if dx equal to B bar minus L plus U x bar. So, now I am writing it as dx into this. If and only if x is equal to D inverse into remaining part. So, now I have got some kind of a clue for my iterative scheme. So, thus if we assume that the diagonal elements of A, AIR are not all 0 for all I equal to 1 to 3 up to n, then taking T equal to D inverse minus L into minus U and C equal to D inverse B converts the system A x bar equal to B bar into x bar equal to T x bar plus C as desired earlier. And the schemes developed by this process is called the Jacobi iterative method. So, we have seen here that if I can write it like this, if you can express this x bar equal to B bar in this form, I can generate the scheme using this kind of thing. So, first I will take x 0 bar will give me x 1 bar, then x 1 bar I will plug in here, I will get x 2 bar, and like that you can generate the sequence of approximations. And this is what we are doing it here, where T is given by this, C is given by this, then this is called as a Jacobi iterative method or Jacobi iterative scheme. We may also generate T and C like this in a different way we are doing now. L plus D U x equal to B bar, if only now I am taking L plus D x equal to B minus U x. So, only upper triangular part I am taking on this side, and then I am taking inverse of L plus D inverse B bar minus L plus D inverse U x. If I write, then I will get another scheme here. So, observe that L plus D is a lower triangular matrix with diagonal elements same as that of A, and it is well known that a lower triangular matrix is non-singular if and only if none of its diagonal elements is 0, and therefore, L plus D inverse will be non-singular and this will exist. And if AII is not equal to 0 for all I equal to this. So, if all the diagonal elements are non-zero, I will be able to get this. So, diagonal elements play a key role here. So, thus the system A x bar equal to B bar is reduced to T x bar plus C. Again I am writing it in this form. What is T x bar now? T x bar will be L plus D inverse into U, that is T x bar I will get, and C bar will be L plus D inverse B bar. So, such a choice of T and C gives Gauss-Seidel iterative scheme. Now, this is all a convenient way to talk about these schemes, but computationally it may look somewhat tedious because you have to compute in inverses and all that. Instead of that, we can write it in the matrix notation, and we can describe these methods in an easier manner like this. So, I am talking about Jacobi method. So, Jacobi scheme, Jacobi method I am talking about. So, consider the system of n linear equations in this. Essentially what we are trying to do here is this, where A equal to Aij is a non-singular matrix, B is this, and so on and so forth, is a non-zero vector in Rn. In Jacobi method, Jacobi iterative scheme is used to generate a sequence of approximation xk to the solution of the system. So, we are using Jacobi scheme. Now, what is that Jacobi scheme? Jacobi scheme is given by xk equal to D inverse B bar minus L plus U x k minus 1, and that is nothing but, if I write x bar k as x 1 k, x 2 k, x n k, and if I can write L plus B minus L plus D I have to write down. So, first I am going to write it in this form. So, B into D inverse. So, D inverse into B. So, this is D inverse into B minus this part. So, B minus this part is this. So, L plus U is nothing but this, only diagonal element will be 0, all other elements of the matrix A as it is into this. So, I get a scheme like this. in when you write it in the matrix form, and if you go into the details, I will be getting x 1 k will be equal to 1 upon a 1 1 into b 1 minus this remaining one. Why? Because you can see here I am taking x 1 k. So, that means I have to consider this. So, I have to consider this row into this. So, b 1 minus a 1 2 x 1 a 1 n minus 1 this x n minus a 1 n x n, that is what I will be getting, and I have to multiply it by 1 upon a 1 1 because the rest of the things are 0. So, I have to simply take only first row and all other rows will be 0. So, I will get 1 upon a 1 1 into b 1 minus this into this, and that is what I am getting here as my first equation. And if I do this for any general j x j, then what will happen actually, I will be getting here two parts I will be getting. So, one part will be below diagonal, other part will be above diagonal, this row will be discussed like that, and therefore, I will be getting here and a scheme like this. So, I will get 1 upon a j j b 2 minus all elements before j, that means below diagonal elements, they are all above diagonal elements, and I will get two sums like this, and x n k will be only I will be getting all below diagonal elements only, because no, that part is not going to be there. So, I will be getting r equal to 1 to n minus 1 a n j x j k minus 1. So, these are all less than n, these all elements are greater than 1, and these elements are, some of them are less than j, some of them are greater than j. So, that is what I am getting. So, this is the scheme which is written in a nice understandable form instead of writing it in a matrix notation. So, Jacobi method, thus the Jacobi scheme is obtained by using the jth equation to express x j in terms of the remaining variables, and then compute kth iteration value of x j by substituting k minus 1th iteration value of the remaining variable on the right hand side for all j equal to 1 to 3 up to n. So, what we are doing is we are expressing x 1 we are taking on one side, and then we are taking expressing x 1 in terms of remaining variables. Now, on this side I am using previous iteration values. So, on this side I am using previous iteration values, and on this side I am using previous iteration values, and x last equation gives me x n k, jth equation will give me x j k, first equation will give me x 1 k. So, like that the iterative scheme can be thought of. So, computations being with initial guess x bar 0 begins with initial guess x bar 0, and successive approximation x bar k are computed in subsequent iterations using formula 3. So, these are my formula 3. The iterative procedure terminates. Now, you have to terminate this iterative procedure if the two successive approximations are as close as desired. What do you mean by as close as desired? So, closeness of two successive approximations, they are vectors. So, each component, by component subtraction I am taking, and I am taking absolute value, and then I am using the maximum of all these absolute values. This is maximum norm of the vector, difference of these two vectors. So, maximum of mod x I k minus x I k minus 1. So, two successive approximation values I am taking, and that I am going to call it as an error. So, this maximum error I am trying to determine, and thus the procedure terminates if my E k is sufficiently small, say small number I am denoting it by C. So, if it is a predetermined positive number depending on the accuracy required. So, if C is small, my accuracy will be better, C is little more, accuracy will be little less. So, you can choose C as per your requirement of accuracy. So, now if I use the example and use this scheme for this example, suppose I do 5 x minus 2 y plus z equal to 9, x minus 3 y plus z equal to 6, 3 x plus 2 y plus 6 z equal to 13 I am taking. Now, then the formula 3 are going to be like this. You can see here x k equal to 9. So, I am taking x from this. So, it will be 9 minus plus 2 y plus z divided by 5. Then I am taking this from here y. So, y k equal to minus 6. So, I am taking it as, because this is minus, I am taking y on this side and this on this side. So, I will get minus 6 plus x k minus 1 plus z k minus 1 and divided by this 3, and that is how I will get z k. So, these are the formula 3 becomes like this, and now I am generating the sequence of approximations. I am taking x bar 0 as 0 0 0. So, first approximation as 0 0 0, then my x 1 x bar 1 will be given by 1.8 minus 2 and 2.167. How do I get that? By substituting here. So, if I put 0 0 0 here, I will get 9 by 5 minus 6 by 3 and 13 by 6, and this together gives me 1.2 minus 2 and 2.167. Now, again I will be using this into the right hand side and get the next approximation here, and that you can verify that it will be x 2 will be given by this, x 3 will be given by this, x 4 will be given by this. So, 4 times I am applying the scheme. You can see here I am also calculating the component by component error, and I am taking the maximum value here. So, maximum error here will be 2.167 for this x 1 minus x 0, then x 1 minus x 2 I am taking here. So, this difference is 1.2 like that, and I will get all these differences like that, and the maximum error becomes 1.322. When you go to x 3, difference between x 3 and x 2 I am writing here, and I will get this, and you can see that the maximum error goes on reducing here after iteration in the successive iterations. So, note that the error reduces as iteration count and k increases, and hence we conclude that the sequence x k converges to the true solution. This may mathematically it may not be, I cannot confidently say that this it will converge, but computationally I can say that okay, error is reducing and my sequence is converging to that solution. In fact, after 22 iterations, so if I run this MATLAB program on this, then after 22 iterations we get exact solution x equal to 1, y equal to minus 1 and z equal to 2, and with tolerance of c value I am getting as 10 raised to minus 6. So, that means difference between the last two successive approximation will be smaller than this. Now, Gauss-Seidel method on the other hand is also iterative method. Only change we are going to do is in the selection of elements on the right hand side. So, what we are doing is consider the general scheme of n linear equations in n general system of n linear equations in n unknowns as considered in the above section. Note that in the kth iteration of the Jacobi method, when the value of x j k is computed, kth iteration values of x 1 k, x k minus 1 k are available. However, only k minus 1 iteration values of these variables are used in the Jacobi scheme. What we are doing here is, in the Gauss-Seidel method, the iterative scheme is similar to the Jacobi scheme, except that the computing values of any variable in any iteration, we use the latest computed values of the remaining variables. So, if you have got latest computed value of the previous variables, I am going to use that, and thus the Gauss-Seidel scheme will follow like this. You can see here, in this case none of the value is available earlier. So, therefore, I am going to use all values are like this, but when I am computing x j k, I have already computed all the remaining values here in the kth iteration itself, kth iteration, and therefore, I am using kth iteration values for below diagonal elements. That means, we are taking before j all the elements I am going to use as kth iteration value, and here k minus 1th iteration value. So, only difference in the Jacobi and Gauss-Seidel is here I am using k minus 1 for Jacobi, k minus 1 iteration values, here I am using kth iteration value. That is the only difference in this, and in the last case all elements at the kth iteration are available. So, I will be using all of them from kth iteration, and then I will get the kth iteration value of the x and k. Rest of the procedure in the Gauss-Seidel method is just the same as in the Jacobi method. So, termination criteria etc., everything will be same. So, again I am considering the same system of equation. My scheme now changes. Here I am taking k minus 1, k minus 1. Here I am using, because x k is available, I am taking x k and k minus 1. Here I am using x k as well as y k. So, that means that is only change in the scheme, and if I use that, I can again start with 0 0 0 and I will get the values like this. You can see here error is 1.8. Here next iteration value will be given like this, error becomes 0.9707, 0.133, 0.066. So, in the fourth iteration the error has become much less as compared to in the Jacobi's method. And you can see here that the E k reduces as iteration count k increases, hence conclude that sequence converges, and in fact 12 iterations we get exact solution after 12 iterations. In the Jacobi method we required true solution after 22 iteration. Here we are doing it, getting it after 12 iterations. So, Gauss-Seidel method is working faster and is going to give you solution little quicker than the Jacobi method. All right. So, convergence criteria now we will be talking about of Jacobi and Gauss-Seidel method. So, the sequence of approximation x k generated by any of the two schemes is said to be convergent if this error tends to 0 as k tends to infinity. If it tends to 0 as k tends to infinity, then only we will say that the sequence of approximation converges. The convergence can also be defined in terms of the error E dash k may be mod x bar k minus b bar. So, that means we are actually substituting it in the system and we are seeing that how much that those equations are satisfied. This is the norm, where the norm is the Euclidean norm of R n, because this is going to be R n vector, Euclidean norm in R n, and however we prefer to use error E k as it is easier to compute E k as compared to this, because here you will have to do matrix multiplication, here I do not have to do that matrix multiplication, E dash k will be considering. So, instead of E dash k we will be considering E k. So, convergence of the Jacobi and Gauss-Seidel method, note that both the schemes discussed above can be defined only if the diagonal elements of the coefficient matrix are non-zero, because I have to always divide by diagonal element. So, however, this does not guarantee the convergence of the sequences of approximations generated by these schemes, which is illustrated in the following simple example. I am taking a simple example here like this. I am taking just two variables. Now, you can see it is easy to note that exact solution of this system, you can solve this system, you get exact solution as 2 by 11, y is 3 by 11. Approximate solution up to 3 decimal places, if I convert it into decimal point, I will get x 0.182, this will be 0.273, in fact it will be 181818, 272727. So, the Jacobi iterative scheme is given by now. If I want to solve this by Jacobi iterative scheme, my iterative scheme will be like this, and I am using this iterative scheme and I am calculating again as previous, we are doing this table calculations here. So, I am taking initial value as 1 1 and then I am getting, these are the remaining values I will be getting. So, minus 2 3 3 4 2 3 10 9 minus 26 minus 39 118 105. So, values are increasing, error is increasing 4 12 48 144. So, that means my sequence of approximation does not converge at all, it is not converging, it is in fact diverging. So, note that the error E k increases in as iteration count increases, and hence we conclude that the sequence diverges. So, solution exists, but this method fails to give me the solution. Similarly, Gauss-Seidel scheme if I use, then it is diverging much faster than that. So, here my error becomes 13,822, which is much larger, and therefore, note that the error E k increases and the sequence diverges. So, here we can see that though the solution exists, our schemes, both the schemes fail to give us the solution. Now, suppose we write the same scheme in the reverse order. So, I am writing it first this equation and then next this equation. In the earlier scheme, what I have written is, first was your equation this actually, first was this and then second. I am now interchanging the equations here. So, if I do that, so I am changing my system like this. Example 3 we are considering. So, this is divergent. Now, I am changing my system like this. So, my now Jacobi scheme will become x k equal to 1 minus y k minus 1 4 divided by 4, y k will be equal to 1 minus x k divided by 3. And you can see the magic now what happens, you can see here that x k y k is 0 0, x 1 y is 0.25, 0.33, difference is this, error is this, x 2 equal to 0.167, 0.25, error is 0.83, x 3 equal to this, error is 0.028, and now x 4 is 0.181, 0.271, and error is 0.007. You can see that the scheme converges, started converging. So, note that the EK reduces as iteration count increases, and hence we conclude that the sequence x k converges to the true solution. In fact, after 12 iteration we get almost exact solution like this, and with tolerance as 10 raised to minus 6. Similarly, one can verify that in this case the Gauss-Seidel scheme also yields the sequence of approximate solutions converging to the true solution of the system. The above example suggests that convergence of the sequence x k of approximate solutions depends on the form of the coefficient matrix, because coefficient matrix changed, convergence we got, coefficient matrix is different, I get divergence. So, what is the property that affects our convergence of the scheme, which is called as diagonally dominant system. So, there are a number of sufficient conditions which assure the convergence of sequence of approximations to the system 1. One such condition is given in terms of the diagonal dominance property of the matrix A. And what is that diagonal dominance property? You know that diagonal element plays a vital role. So, I want that diagonal element to be very large as compared to other elements in the matrix. So, that is what called the diagonal dominance. So, given n by n matrix A, Aij equal to n cross n is said to be diagonally dominant or row diagonally dominant, strictly row diagonally dominant if mod Aii, that means diagonal element in absolute value, is greater than sum of the absolute values of the remaining element in that row. That means diagonal element is sufficiently large, then my theorem says that given the system of equation 1, if the coefficient matrix A is strictly row diagonally dominant, then the sequence x k of approximate solutions to the system generated either by Jacobi or Gauss-Seidel iterative scheme converges. Both the schemes will converge provided this condition is satisfied. For a simple proof of this theorem, you can refer to reference number 7, which is given in our additional reading material file. Results can be stated in terms of the strict column diagonally dominant also. Similar result I can state it in this strict column diagonal dominant. That means, you have to take diagonal element to be maximum in that column. For the detailed discussion on this, you can refer to the reference number 14 from the additional reading material file. Now, diagonally dominant system when you are talking about, note that in example 1, the initially given system has coefficient matrix 1 3 4 1, which is not row diagonally dominant, and by changing the order of the system of equations, the new system is such that new coefficient matrix becomes strictly diagonally dominant. If this goes here and this goes here, 4 1, so 4 is the diagonally dominant. So, 4 1 1 3 becomes diagonally dominant, and therefore, we have got the convergence. This suggests that if initially the matrix A is not diagonally dominant, it may be possible to permute the rows of the matrix A to convert it into a diagonally dominant matrix. However, this may not be always possible. Even after interchange of rows, the system may not be diagonally dominant. So, we are looking at example 4 here. Another important point is the strict row diagonal dominance is a sufficient condition, but not a necessary condition, which can be seen from the following example. So, this is a sufficient condition, not a necessary. Necessary means what? That convergence, if the scheme converges, does not mean that system has to be diagonally dominant. Okay, you can see here, consider this system I am considering. Again the formula 3 Jacobi scheme I am taking, x k is given in terms of this, and then we are saying that note that the coefficient matrix of the system is not diagonally dominant. Is it diagonally dominant? You can see here coefficient matrix 4, 2, 1, this is fine, but this is not diagonally dominant, because this value 2 is not more than sum of these absolute values of these two values. So, therefore, this system is not diagonally dominant, and true solution, exact solution of the system is x equal to 1, y equal to 1 and z equal to 1. If you substitute that, you can check 4 plus 2 plus 1 is 7, minus 1 plus 2 plus 2 is 3, 1 plus 4 is 5. So, 1 1 1 is the solution of this system. It is shown that the sequence of approximation generated by the above scheme starting with the initial guess x 0 as given in the following table converges. So, you can see here that this is convergent. Again you are generating, this is the starting point, and you are trying to generate this scheme, and we are getting this. So, you can see here, note that the error reduces as iteration count increases, hence we conclude that the sequence x k converges to a true solution. So, note that x 4 is quite close to true solution, because x 4 you can see here 1.0835, 1.0325 and so on and so forth, which is close to exact solution. In fact, after 28 iterations we get exact solution as given by this with that tolerance, and the Gauss-Seidel scheme also converges in 16 iterations. So, we get here convergence in 16 iteration for Gauss-Seidel and this. In general, Gauss-Seidel scheme converges faster than the Jacobi scheme. However, there are systems of equations for which Jacobi scheme converges, but Gauss-Seidel scheme fail to converge. For example, see the following illustration given in the sequence reference 7 given in additional reading material file, and you can this is the example directly given, I am taking from that book. So, minus x plus 0.5 y plus 0.5 z equal to 1, 0.7 x minus y and this equal to this, and 0.3 x minus y minus z equal to 1. For this system, Jacobi scheme converges in 76 iteration. If you apply this your Gauss elimination algorithm for that, then I will get this, and Gauss-Seidel scheme failed to converge even after 300 iterations. So, nothing certain can be said about these schemes. When only certain thing that we can say is that if the system is diagonally dominant, both the schemes will converge. Nothing more than that can be concluded. We can make more this general statements like this, that Gauss-Seidel scheme will be faster than Jacobi scheme, but then there are counter examples here which says that Jacobi scheme converges, but Gauss-Seidel scheme does not converge. Anyway, algorithm Jacobi and Gauss-Seidel. So, now we are writing computer algorithms, and that will be fairly easy. This algorithm takes n coefficient matrix A, right hand side vector B bar and initial approximation x bar 0 to the solution of the system of linear equations this as input, and compute successive approximation x bar k to the solution using formula 3 for Jacobi and formula 4 for Gauss-Seidel method. The algorithms terminate if the two successive approximations, that is this maximum error is sufficiently small, measured in terms of this is sufficiently small. The algorithm Jacobi and Gauss-Seidel. So, again we are doing that. So, thus the algorithm terminates if E k is less than C, where C is a small positive number depending on the accuracy required. Now, since there is no guarantee of convergence of the sequence of approximations unless the system is diagonally dominant, maximum number of iterations are fixed in advance, and if the sequence of approximations does not converge within that limit, then we will say that algorithm will terminate will giving appropriate message. So, we make sure that it does not go into the infinite loop. Now, algorithm 13.1 I am writing it in this form. So, size of the matrix, then this matrix, the right hand side vector, all these things are taken as input. The tolerance for the difference of two successive approximation C is taken as input. Maximum number of iterations to be performed, I am writing it as max iter, that number is also taken as input, and initial guess to the solution of the system is taken as input, and we are calculating output vector in this form. So, we indicate non-convergence. Output will be either you get the solution or you indicate the non-convergence. So, these are the two outputs we are doing. Iterative steps are like this: initialize p x, that previous x as x, and for j equal to 1 p x j equal to x 0 j, we are storing it in previous x, and then current x we compute using the scheme. So, perform at the most maximum iterations of this. So, for k equal to 1 to max iter, I am taking for j equal to 1 to n and x j equal to b j first we are writing, and then we are computing this r equal to 1 to j minus 1. The first sum we are doing here, and then second sum is calculated in this for loop, and then whole sum is divided by a j j. So, that I will get x j. So, E is equal to maximum of x j and previous x j, we calculate error after that, and if E is less than C at any stage in the performance of the outer loop, I will get will say that print solution is this, either you get solution convergence, if it is convergent you get print a solution and come out, then you can say that algorithm terminates here. If not, then we will go to the next iteration. So, we will make your current solution as your p x j, this should be x j not x 0 j. So, we are taking p x j as x j, and then again you go on computing this. So, print sequence x k does not converge if after that, if even after maximum number of iterations you have not come out of the loop, then we will be printing this. So, that means that it will indicate that the algorithm has not converged within the given number of iterations, and an algorithm terminates. Only change in the Gauss-Seidel will be the first sum here for summing from j equal to 1 for r equal to 1 to j minus 1. I have to use here new values of x r, and in the earlier case we are we were using p x here. We are using p x j. Actually, p x r we are using in both the loops. In first loop we will be using x r, and in the next loop we will be using p x r for Gauss-Seidel. So, that gives me algorithm Gauss-Seidel. The time complexity of these algorithms is easier. We measure the time complexities in terms of A, M and C, and this time complexities we are getting these are the times required for addition or subtraction, multiplication or division, and comparison, and then we compute it like this. Observe that the for loop for k is evaluated max iter times, and in each execution of the loop one computes n components of x k, and then compute error E and compute it with C, compare it with C. These are the things that are the tasks that we are performing. Now, computing each component of x k requires n minus 1 multiplication and n minus 1 subtraction operation, and for computing E and comparing with C requires n subtraction operations and n comparisons. Thus, the time complexity required will be T n will be equal to max iter times n into n minus 1, because those many components we are finding out, into a plus m into n into a plus c. That is what we are doing, and therefore, the asymptotic time complexity of these methods will be order n square as compared to your Gauss elimination algorithm. It is order n cube. So, here order n square. So, thus in this module we have discussed Gauss-Seidel, Jacobi and Gauss-Seidel iterative schemes, for finding the solution of the systems of linear equation. The convergence of the sequence of successive approximation has been discussed, giving relevant illustrations, and in the process strict row diagonal dominance of the coefficient matrix is defined and stated that an important result that strict row diagonal dominance assures the convergence of both the schemes here, and in the Jacobi and Gauss-Seidel algorithm have been stated and their time complexity have been computed. So, this is what we wanted to do regarding the systems of linear equations. I think we will discuss, we will end our discussion on systems of linear equations with this module. Thank you.